Welcome to Power System Protection course, module on distance laying. In this lecture, we will address protection of series compensated line. This is part 1. So, this coverage in this one will be concepts on the issues with series compensated line, protection perspective, current and voltage inversions, and how these issues create problem in directional laying, and what is the solution approach that we will see. So, see this system, simple system, 2 bus system. We have a now series capacitor in the system. Series capacitors being minus of j x c, the corresponding reactance as compared to the j of x l of the line or j of x s for the source. So, this reduces the reactance of the network including the fault loop. This is being widely used for numerous reasons. Number 1, it increases the power transfer capability because equivalent X of the transmission system reduces, enhance voltage control as a drop in the system network system will be reduced, X equivalent in decreases and I of X equivalent will be small. So, drop will be also small. Flexible power flow control, if you have a double circuit line and if you have series compensation, if in one of the line, then you can, if you switch on the series compensation in the circuit, that one of the line will be having more power than the other one, or if you have a controllable capacitor, you can control as per the requirement. So, these capacitors can be installed at the line ends here at this end also or at both ends, or can be installed at the any intermediate point in the line. But generally line ends are preferred because we do not need further more substation and so. Percentage of compensation is defined in terms of the value of x c upon x l, the corresponding line to which it is connected. Typical compensation level varies from 25% to 75%. In special cases, it may be more also. Now, for this capacitor of its own, there is a of its own protection arrangement, like each capacitor in each phase may be a bank of capacitors connected in series and parallel to have the required capacitance for the particular compensation. Now, these bank of capacitance, they are being protected by, as in the diagram, metal oxide varistor MOV, which happens to be a nonlinear resistor, which functions whenever a voltage across the MOV increases, the resistance becomes significantly low and therefore, the current through the MOV becomes high, and this gives a scope, you can say that, to bypass the circuit to which it is connected. We have a spark gap, controllable spark gap, and then we have a bypass breaker. Now, what happens in this case? This is the line to which the capacitor is connected. So, if this side is source and this side is having a fault here in the network, then the current path in the fault loop reactance becomes significantly low because of this minus of j x c, and that is why the current becomes very high. So, when the current becomes high in this through this capacitor, the I x drop across the capacitor becomes very large during the fault, and thereby the voltage across the MOV becomes high. So, the MOV triggers immediately, and the corresponding current, significant current passes through this, and thereby the corresponding current through this capacitor decreases and the voltage is being clamped. This saves the capacitor from possible damage. Now, following this spark gap now functions. The temperature of the MOV increases, the energy contained in the MOV increases, and following a threshold on the energy associated, the spark gap is being ignited, and the spark gap leads to a bypass of this MOV also. So, the spark gap bypasses the MOV and the capacitor, and thereby the corresponding voltage across become very negligible. Following that, the bypass breaker operates, and this saves the corresponding capacitor from high voltage issue. And note that the corresponding capacitor is in the circuit normal time. If a fault happens to be there and the corresponding current becomes significantly large, the corresponding capacitor is being bypassed by this protection arrangement. So, the corresponding current through the capacitor becomes when it becomes more than 2-3 times the full load current, the R gap ignites, and within less than 10 millisecond, but before that the MOV also operates immediately. So, with this functionality of the protection arrangement of the capacitor, the corresponding relay at this bus will see the corresponding current and voltage pattern, because the corresponding X of this capacitor will be modulated by this functionality of this MOV, spark gap or the bypass breaker. Now, this arrangement leads to transmission line protection. MOP may operate or may not operate. MOV will operate if the current become more than 2-3 times in the fault path, but for lower current due to very remote fault or fault associated with any arc or high steep fault, the current may be low, and then the corresponding capacitor may not be bypassed. MOV operates, following that the corresponding air gap ignites. These phenomenon lead to change in equivalent reactance, and therefore, the corresponding current and voltage across the capacitor, and so also at the relay point. Line protection scheme must take care the operation, these operations. So, where capacitor may be there in the circuit and capacitor may not be there because of the bypassing by these arrangements. Furthermore, the introduction of C in the line, which has the line has series inductance. So, this LC combination gives us subharmonic frequency component oscillations. So, therefore, in the signal as seen by the relay will be having these components, and which will affect the phasor estimation process, as we have studied in the phasor estimation by one cycle DFT or so. So, the frequency response of that we have seen that subharmonic component affects the performance of the phasor estimation technique. Furthermore, because of this air gap and the MOV operations, the transients will be introduced, high frequency transients will be introduced in the signal, but we have anti-aliasing filter and the before the processing by the digital components. Therefore, they do not have any issue to the numerical relay performance. The challenges which you will see in the directional link or line protection perspective, two aspects, one in the distance relay itself, and we know distance relay also requires directional features, maybe a separate directional algorithm also. So, that you can say that component is also affected by this presence of the series capacitor in the circuit. We will like to analyze. In this lecture, we will address only the directional link part. In the next one, we will talk about distance relay. First phenomena which is being there, which will be there in this series capacitor, presence of series capacitor, we will try to analyze that. This phenomena called current inversion phenomena. Now, let us consider a system like this, where we have a series capacitor at the M bus end, where we have the relay. Already pointed out, the capacitor can be at this bus also, or both also, or in the middle also. But this analysis also can be extended to any other position of the capacitor. Now, if fault happens to be there at F point in the line, which has a reactance up to from the relay bus to this fault point J of X L F, and the corresponding capacitor having a reactance of minus J of X C. The equivalent circuit diagram for this system and becomes this up to the fault point, let us say 3 phase fault. So, we have V s and the corresponding J of X s of the source and the bus, and minus of J X C and J of X L F. So, this path now having an equivalent reactance of J X s minus J X C plus J of X L F. We have neglected resistance for simplicity. Current through the relay bus at M for this situation will be the V s upon J of X s plus X L F minus X C. Now, normally this X C is not present. So, we have V s upon J of X s plus X L F. So, this part becomes a positive part, and we say that the corresponding relay current lags the voltage by close to 90 degree. Ideally, it should be 90 degree. Now, what happens in this presence of this X C, this part, there is a chance of this part can be negative. So, when this X C becomes greater than X L F plus X S, this combination, this becomes negative. So, it means that as compared to the normal case, the corresponding current will be in antiphase. So, that is what the issue. So, normally we see that the current lags the voltage during a fault like this, but with the presence of X C, and if this condition is being satisfied, the current will lead and it will be around 180 degree out of phase to the normal current which we have seen in earlier analysis. Because the corresponding current is being inverted, we call the phenomena as current inversion phenomena in a series compensated line. Now, for this one we like to consider have this phasor diagram to have our clarity and to have our further analysis on different relay applications. So, same circuit. So, P C you consider suppose V s, this is V s. So, we know V r equals to V s minus J of X s I r, right, if this relation. So, V s, so before the fault, the line was feeding to certain inductive load or slightly inductive load or so. It has connected to the further line and so. So, circuit will behave like inductive circuit. So, therefore, you can say that I r V s minus this drop. So, this I r you can say that the let us say I pre is very close to this V r pre. with drop in this part will be leading to this I pre j of excess I pre. So, therefore, if you subtract that drop, then this will be minus of j excess I pre like this here, and then this becomes equals to V pre. So, before the fault, the position of V pre lags the V s by a small angle, as you know. So, this is pre fault issue. Now, come to the fault issue. So, we have the same V s. Now, from the earlier analysis, we say that the current will be inverted. So, the capacitor would not be there, the corresponding current would in the fault path will be lagging current almost 90 degree ideally. Now, that will be inverted because of that X c greater than X L plus X f, and that leads to consider the corresponding inversions to be the current direction will be like this with the presence of the capacitor if that condition is being satisfied, X L greater than X L f plus X s. So, in that case, because we are talking about current inversion case, so in that case the corresponding current direction, fault current direction will be upward in this phasor position, and then you can say that the drop here you can say that will be as usual minus j x s I r again. So, therefore, minus j x s I r. So, this part you can say that will be to the right hand side anti-clockwise. So, this is minus j x I r f in this side. So, if we add this you can say that V s and minus j x s I r f, then the corresponding V r f becomes this. So, this is the position of V r f what we see. The immediate conclusion we see here, because of this phasor position in the upward direction, so the corresponding V r f fault relay voltage during fault during current inversion situation becomes a larger value as compared to the pre-fault voltage, as compared to the pre-fault voltage at the relay position. So, this is the peculiarity we observe. Normally, we see you can say that during fault time there will be a drop in the system, this part in the source side, and therefore, you can say that the corresponding voltage of the relay bus voltage will be smaller than the pre-fault voltage. But now, we see that a larger voltage due reason is the current inversion. So, during current inversion the voltage becomes more than the pre-fault voltage, but the current is now leading even though the corresponding fault is forward, which is the difference. Earlier, without the capacitor, we are considering that the corresponding current will be lagging to this voltage almost 90 degree or so. Now, we will go to another phenomenon called voltage inversion, like we discussed on current inversion. Same system. So, we have relay here as we see here, and then the equivalent circuit diagram becomes this. Now, what circuit condition leads to a different situation, we like to figure out that. So, voltage seen by the relay at bus M. Now, we will calculate the voltage seen. So, already we have mentioned the I r through this is V s upon j x s plus x l f minus x c. The V r, this voltage for the 3 phase fault case, consider that this point voltage is 0. So, therefore, you can say that the corresponding voltage of bus M will be, if I r current is through this part, I r into j of x l f minus x c, I r, because I r direction is this, I r into j of x l f minus j of x minus j minus x c. So, these were the relation. So, the voltage relay bus P r becomes this. If you substitute this I r here, then in terms of V s, the V r becomes equals to V s into j of x l f minus x c upon j of x l x s plus x l f minus x c. Now, what we see here, that we will have a voltage inversion like the current inversion condition, that this part becomes positive, but this part become negative. Now, how? If the x c is greater than x l f, so this becomes negative, and this x c is less than x s plus x l f. Once again, that the fault point, up to the fault point, the corresponding impedance should be smaller than x c, first condition. Second condition, the denominator, this part becomes positive. How? When the Xc is smaller than Xs plus XLF. So, this is a combination of the source side impedance plus the fault impedance up to the fault point. If this condition is these two conditions are being satisfied, then what happens we see here, this part becomes positive, but this part becomes negative, j cancels out. So, finally, this becomes equals to with a negative sign of V s with certain value, whereas in normal condition if this X c is not there, then it becomes j cancels out and this becomes positive value, this becomes a positive value. So, V r and V s are very close to each other, that we have learned. But now, with that these two conditions we see here, this becomes negative, this becomes positive. So, therefore, we can say that a negative sign will come here, which is nothing but the antiphase or the corresponding inverted voltage, and that is the situation. So, that is the name voltage inversion. So, we see that current inversion for a particular condition of the circuit, and we have voltage inversion for a particular situation of the circuit. Now, similar to the current inversion, for the corresponding phasor diagram for the voltage inversion, same network. So, we have V s minus of j x s I pre. So, this becomes V pre as observed by the relay bus by the relay. Now, the corresponding current through this path is lagging here, because of the denominator being positive, x l minus j x c, x l minus x c plus x l f. So, that becomes positive. So, current will be lagging. So, this is a lagging current in this case. Now, to this lagging current, if this I r you can say that is this lagging current. Now, our point is that the voltage here is I r into this drop, which happens to be a negative. So, I r into this drop. So, that gives us this part, so j of this. So, therefore, you can say that this becomes this, but this x c is greater than x l f. This x c is greater than x l f. So, therefore, you can say that this becomes takes a position like that as compared to this. So, that leads to you can say that you can say the corresponding this. Now, if you suppose you can say that the corresponding x l f x c is not there. So, j r f into x l f. So, that is positive j. So, 90 degree anticlockwise it would have taken a position like in the around V s. But now, because this x c is greater than this, so this will be antiphase to that V s close to that, and thereby I can say that it takes the V r f, the voltage at the relay bus takes a position like this, and that is the name we call voltage inversion. Usually the corresponding fault voltage remains like in this close to this V s V pre, but now you can say that it will remain not V s the V pre, but now you can say it is remaining almost 180 degree out of that. Generally, you can say that this voltage inversion results in the voltage phase angle more than 90 degree, 90 to 180 degree kind of thing during fall for the voltage inversion situation. But note that this circuit diagram we discussed for the 3 phase fault case, but faults can be phase to ground, double phase to ground or double phase fault. But in other networks, other faults, the positive negative zero sequence components they adopt depending upon the types, and thereby they offer larger value of x of the rest of the system, larger value of x for the rest of the system, and therefore, you can say that voltage inversion is not that common in other types of fault as compared to the 3 phase fault perspective and so. However, whatsoever the protection schemes cannot ignore, you can say that such situations. So, we see here what are the current inversion and the corresponding voltage inversion. Now, these has direct implications to directional relay. So, we will see first what are the issues with directional relay. So, the phasor diagram we have already seen for the current inversion. So, in case of current inversion, the corresponding current becomes upward with respect to this V r f, the V s or the V r pre leading current, whereas usually it should be lagging current. Now, if you see, you can say that the corresponding things now as compared to that, the in case of with capacitor with respect to this relay voltage, the corresponding current becomes leading. but the fault is forward fault. So, therefore, we say here you can say that this will create problem to the directional link based on phase components, based on Poitou sequence component approach and so. Whereas, normally it should be lagging, and because the directional link approach we have discussed is based on the sequence component of current, based on the sequence component curve, phase approach and so. So, that is why you see can say that here we expect this angle based directional link is expected to be affected by this issue. Now, in the voltage inversion case, if you see here the corresponding voltage becomes antiphase to the normal voltage phase position. In same like that, we see that the corresponding current now leads the corresponding voltage, even though the fault is forward. This will also create problem in this perspective also. So, in both cases we see that current leads the voltage, and that is the issue, whereas it should lag in normal as in the normal system. There are other points to be noted. When the fault current is high, MOV operates, resulting in lagging current, means the capacitor is bypassed, so resulting in lagging current. So, this inversion process may last for few milliseconds to within a cycle in the system. In case the fault resistance is high, the MOV may not operate. In that case, the capacitor will be in the circuit and the system may observe the corresponding current inversion and voltage inversion. So, therefore, the relay algorithm, the protection scheme should be equipped with both the possibilities. Some of the solution strategy, if we see the corresponding voltage inversion issue, then instead of taking the voltage at this point, if we measure the voltage at the line side at this point, so fall from this side, the corresponding voltage calculation will not consider inclusive of the capacitor, and thereby the system will be behaving like as usual what we have seen earlier. So, if we can avail the corresponding line side voltage, then the voltage inversion phenomena for this case will not create any problem to the directional link approach. The other you can say that solution is the memory voltage. If you see this, in this case, if we use the corresponding pre-fault voltage, not the fault voltage, then our problem is solved. If we use the pre-fault voltage, not the fault voltage, then is solved. However, pre-fault voltage can be used to certain period of time, because of the issue of frequency drifting with the time during the fault and so. Therefore, you can say that you cannot compare the phasors during fault to the pre-fault value, and other issues are also there. Now, we will see through examples the corresponding issues and how they affect the directional link, and then we will see what is the solution strategy also for the directional link perspective in the presence of current and voltage inversion issues. 3 phase fault in a 2 bus system, 110 kV 50 R system, 3 phase fault to create current and voltage inversion issue. We have pre-fault data, we have fault data, balance system. Now, fault data, 3 phase fault, current rises significantly, but you see voltage also rises in each phase. So, voltage rise from the pre-fault clearly indicates this is a current inversion phenomena that we have already analyzed. We computed this corresponding I 1 and V 1 for the pre-fault and fault, I 1 and V 1 for the fault case also. In the phase based approach, or can say that in the Poitou sequence based approach, if you see this Poitou sequence perspective, so Poitou sequence voltage having minus 1.55 and the corresponding current is 64.10 degree. So, angle of I 1 minus angle of V 1 is phi 1, which we have already used in our directional link principle. that becomes 65.65 degree. Note that this positive angle implies reverse fall, whereas this is a forward fault. So, that means that the positive sequence based approach fails in the case of, you can say that current inversion situation in the circuit. Note that this is current inversion, and if you see, you can say that the corresponding case. So, the V 1 f and this I 1. So, the I 1 is leading, and that clearly shows that this is a situation of the current inversion. In the phasor diagram, we saw that current inversion has two issues. One is that the voltage rises, and the other is, you can say, the current also leads the voltage. So, the current inversion, what you mean that if it have been normal line, then the current should lag the voltage, but now you can say that the current may lead, you can say that with significant amount to the voltage. Now, we will go to another example on voltage inversion. Same system, 3 phase fault again, and we have pre fault data, set of measurements for voltage and current, the corresponding positive sequence current and positive sequence voltage calculated, and the corresponding fault data IA, IBIC, significant amount of current, VA, VBC, and the corresponding positive sequence. Note here, the voltage is smaller than the pre fault voltage. So, this is not a current inversion phenomena. Now, if you see this, you can say that phasor positions. So, this you can say that you see V 1 pre, I 1 f. So, with respect to V 1 pre, the current is lagging, but in case of V 1 f, the corresponding, you can say that current is again leading. So, this means that this is a voltage inversion situation. Voltage is smaller than the pre fault voltage. Now, if we compute this phi 1, angle of I 1 minus angle of V 1 that we do for the directional link, that this clearly shows that this angle is again positive. So, this positive angle means should be a reverse fall, but this is a forward fall for this relay at this position. So, therefore, you can say that this method of positive sequence approach fails. Note, in case of current and you can say that voltage inversion phenomena also, if you see the phase based approach also, because the current is leading, you see here you can say that in this is minus 97 and this is minus 45. So, the current is leading. So, this phase based approach will also fail in the voltage inversion and so also in the current inversion. So, the conclusion from these two examples is that phase based approach or positive sequence approach will fail in case of voltage and current inversion situation. So, therefore, even if a series compensator line is there and if the series compensator line has issue of current and voltage inversions, then phase based or the positive sequence based approach of directional line principle cannot be used. Now, come to superimpose based approach. So, superimpose based approach if we see, so we have, you can say that positive sequence superimpose approach, the equivalent circuit diagram, common circuit diagram. For other faults and all these things, you can add, you can say, to the other sequence components also, depending upon the types of fault. 3 phase fault means you can say that it will be only having this positive sequence component. So, we have already learned that the corresponding in this relation delta V 1 m upon delta 1 m equals to minus j x 1 s. The current is like this. So, minus delta m j x 1 s equals to delta V m. So, with this we see that the corresponding angle of this part equals to angle of this part. So, therefore, angle of delta V 1 m minus angle of delta 1 m equals to angle of minus j x 1 s. This we have already seen our derivations and analysis for the directional link part. What you see here, the capacitor part is to the right hand side of the bus relay position, whereas this j x 1 s you can see that to the left hand side. So, the superimposed component, as you have already seen earlier also, that the superimposed component sees the back side source side. So, therefore, because there is no modulation in the source side reactance, so the superimposed component will see the corresponding direction properly unlike that of the Poetis-Hughes approach. For the current inversion case, what we have discussed earlier, we have already computed V 1 I 1 and V 1 I 1 for the same example. So, compute the delta V 1 from this V 1 f minus V 1 pre delta V 1, I 1 f minus I 1 pre delta I 1, and then our delta phi 1, which you calculate in terms of delta V 1 minus angle of delta V 1 minus angle of delta I 1, that gives us 29.78 degree. So, this minus this angle gives us 29.78 degree. So, this angle is now negative, we say that this is a forward fault. So, this is what we talk about. So, it means that the fault is in forward fault and the approach of Poetis-Hughes superimposed component correctly identified the fault, and we justified that in earlier slide, that because the corresponding approach sees the source side impedance angle, and therefore, it does not have a problem if the corresponding capacitor even in the presence of the capacitor also. For the voltage inversion case, similarly for the same sets what we have seen earlier, the delta V 1 and delta I 1 are calculated, and then we found that the corresponding delta V 1 and delta I 1 are this, and we found you can say that these corresponding phasor positions you can say lagging. So, here also you can say that because the angle is negative, the fault is in forward fault, and then the relay algorithm based on the Poetis-Hughes superimposed component finds the fault properly. Now, think of now the negative sequence approach, which we talk in more details in the directional link also. So, this is the negative sequence diagram, and we use you can say that V 2 m equals to similar to the superimposed component minus I 2 m into j of x 2 minus I 2 m into j of x 2 s, and here also the phi 2 angle you can say that angle of I 2 minus angle of minus of V 2 m equals to angle of j of x 2 s, and this also you can say that nothing but depends upon the source side impedance angle only. So, therefore, you can say that this method is also not affected by the presence of the capacitor, which happens to be the right side of the relay bus in this situation. But inversion rarely happens, you can say that for other types of faults besides 3 phase, as we have already talked about. And however, if the negative sequence is available during certain situations and the inversions are there, then negative sequence can find the direction of fault correctly. So, in overall, we say that series capacitors create problems to protection issues, as it modulates the reactance significantly. Furthermore, the transient associated and the subharmonic components may also interfere to the phasor estimation process. We see that directional leakage has issues because of the current leading as compared to the current lagging for the forward fault case. Solutions: simple solution, use line side voltage or pre-fault voltage for voltage inversion issues, or use the superimposed component or the negative sequence component if available for any inversion issues. Lecture we will see how series capacitor affects the distance relay apparent impedance calculation perspective. Thank you.